All right. For those of you who don't know me, my name is Jasmine. I am the communications intern with Northwoods and Waters of the St. Croix Heritage Area. But what our organization seeks to do is unite the people of the St. Croix River watershed on behalf of our shared natural, cultural, and historic resources. Here's a quick rundown of what all entails the watershed. And then our goals are to create sustainable economic opportunities, connect the region, and increase awareness and understanding of our heritage stories and those resources. And then this map is all of the national heritage areas within the United States. As you can see, there is not any in Minnesota or Wisconsin. So let's put the national into our name. All right. And then I would like to introduce Dr. Marcia. Dr. Marcia Bjornerud is a structural geologist whose research focuses on the physics of earthquakes and mountain building. She combines field-based studies of bedrock geology with quantitative models of rock mechanics. She's done research in high Arctic Norway and Canada, as well as mainland Norway, Italy, New Zealand, and the Lake Superior region. Bjornerud is a fellow of the Geological Society of America and has been a Fulbright Senior Scholar at the University of Oslo, Norway, and University of Otago, New Zealand. A contributing writer to the New Yorker, Wired, and Wall Street Journal and the Los Angeles Times, she is also the author of several books for popular audiences, including Reading the Rocks, the Autobiography of the Earth, Timefulness, how thinking like a geologist can help save the world, and Geopedia, a brief compendium of geologic curiosities. Timefulness was longlisted for the 2019 PEN/E.O.Wilson Prize for Literary Science Writing, as well as a finalist for the LA Times Book Prize in Science and Technology. And with that, I will give it over to you, Marcia.
Thank you, Jasmine, and hello. We're a small, cozy group, it looks like. um, this evening, I was going to do two things, give you a little overview of the geology of the St. Croix watershed, and then read a little bit from my newest book, which is called Turning to Stone, Discovering the Subtle Wisdom of Rocks. And as you'll see, some of the rocks in the St. Croix watershed are featured in my book. I grew up in Menominee, Wisconsin, so not too far away. So I will share my screen. And since we are such a small group, if you'd like to ask questions as we go, that would be very natural to do rather than waiting to the end. It makes a lot more sense to have a conversation now. So I'm happy to do that. So I teach at Lawrence, as Jasmine, I think, said, and miss the topography of Western Wisconsin. We're on the bed of glacial Lake Oshkosh over in the Fox River Valley, and it's terribly flat. So I wanted, as I said, to give a very quick overview of the geology of the watershed. And really, there's about 1 billion years of geologic time represented, but with some big gaps in between. And there are three main chapters, each separated by about 500 million years. So this is a less good version of the watershed map that Jasmine showed. And as you'll see in the slides I have, since I'm based in eastern Wisconsin, I don't normally think of Minnesota's geology too much. And it's ridiculously hard to find maps that show the two states. There is no geological discontinuity really between the two states, but it's very hard to find geologic maps that include both. So most of my maps are going to show the Wisconsin side, but the same things apply to the Minnesota side. So one just big idea about the way geologists see the world is a metaphor that I've taken from medievalists. I have a good friend here at Lawrence who's a medieval historian, and she uses this word a lot, palimpsest texts. So maybe you're familiar with that word. It's kind of an arcane thing, so I'll explain it. Many medieval manuscripts were written on parchment, which was very laborious to produce. And so it wasn't just discarded, it was usually reused. So parchment is tough enough, it's made from animal skins, that you can ink it and then actually scrape the writing off and then re-ink it. But typically in that scraping process, not all of the older writing would be erased. And so many texts, including, I guess, all of the work of Archimedes that we still have access to, exist only as these palimpsests, which are the vestiges of the earlier writing underneath some subsequent writing. And to me, that's a perfect metaphor for the way we can think about landscapes, that they are palimpsests that have been written and partially erased many times over. And if we are able to tune our eyes to those different erasures and overwritings, we can read many layers in the landscape. So if we do that with Wisconsin and adjacent areas of Minnesota, again, what we see is the modern landscape, of course, on the left. This is just a shaded relief map of Wisconsin. You can really see the difference between the driftless area down here in the Southwest, where glaciation did not bevel everything off, and the rest of the state. And then next to it is the Ice Age deposits map. And the Ice Age, I always tell students, happened just the other day, basically. It only ended 10,000 years ago, which geologically speaking is very recent. There may have been people in the region already by that time following the edge of the ice. So the map on the right is showing in red the margins of the last great ice advance, probably about 18,000 years ago. These are terminal moraines. And then we see some recessional moraines or slight re-advances of the ice further to the north from there. And this is really what has shaped the shape of the watershed. If you compare these two maps, you can really see that the boundaries of the watershed in Wisconsin pretty closely follow those terminal moraines. This is a more recent moraine of the very, very last ice advance in the Lake Superior region that really forms the northern boundary of the watershed. It's a continental divide. It's dividing waters that flow into the Great Lakes from waters that flow into the Mississippi. And then likewise, the eastern divide is also one of these moraines. So the last tongues of ice that pushed material from Canada down into our part of the world left these big ridges that today dictate the way that rivers flow. So again, that's the most recent chapter. It's very obvious in the landscape. It's still very much dictating the way the rivers are flowing. Then we go back to the youngest bedrock that we have, and this takes us back to about 500 million years ago, so order of magnitude difference in time, to the Cambrian time. And on this map of Wisconsin, about 25% of the surface of Wisconsin is underlain by sandstones of Cambrian age, around 500 million years old, that were laid down when this part of the world was on the edge of ancient North America. Nothing to the east and south existed at this time, and so we were coastal property. And these sandstones represent ancient wave-washed beaches on an earth that did not yet have any land plants. There were photosynthesizing algae in the oceans, but there was no land vegetation yet. Plants had not evolved. And these are the rocks that you can see at Interstate State Park on both sides of the river. On the Minnesota side, if you go up the Sandstone Bluffs Trail, these are these beautiful beach sands, Cambrian age, about 500 million years, very beautifully exposed. And they're almost pure quartz, beautifully rounded, and in some cases, barely even cemented. You can just break it apart in your hand and you can say, yes, this is beach sand. And then if we go to the earliest bedrock chapter of the St. Croix River Valley, we're back in what is sometimes called the Precambrian, although it's a word I don't like to use because the so-called Precambrian is actually 8/9 of all of Earth's history. It's kind of a misnomer. It just happens to be before the Cambrian. And in Wisconsin and Minnesota, we actually have a very, very long record of different times in the Precambrian that represent almost 2 billion years of time. But the rocks of the St. Croix River Valley are up here in purple, and they represent a great rifting event when North America, as it was a billion years ago, nearly split in two. And this map on the right shows the extent of this great mid-continent rift. A good modern-day analog would be the East African Rift Valley, where Kilimanjaro is today. It would have actually been a high area with volcanoes, but high only because it was hot. What is happening tectonically is the crust is becoming very thinned by faulting. And if this had continued and the continental crust had been completely disrupted, there would have been an ocean basin opening up along this line. But for some reason, it's not completely well understood, that did not happen. And we're left with just this immense thickness, primarily of basaltic lava flows, rocks now, that define this stripe. And these rocks are very well exposed up in the Lake Superior region, up on the North Shore in Minnesota, up in the Keweenaw Peninsula, in the Upper Peninsula of Michigan, and in the St. Croix River Valley. But they can be detected geophysically, even though they're deeply buried under younger rocks, as far south as Kansas and possibly even Oklahoma, because these rocks are very dense. They can be detected by differences in the pull of gravity from place to place, and they're also very magnetic. And so even though they're deeply buried under younger sedimentary rocks, aeromagnetic surveys can detect their presence deep below. So we know that this was a continental scale rift, and it produced just immense volumes of basaltic lava flows. And here are a couple of other maps, just to give you some sense. These are older Precambrian provinces on the left here that had formed prior to the rift. And then you can see how this mid-continent rift kind of disrupted them and nearly ripped this whole area in half. And then here's my attempt to graft together the Minnesota and Wisconsin geologic maps. Unfortunately, geologists can never agree on which colors to use for different rock types. So it looks like there's a big discontinuity as we cross the border here, but it's just because different map colors have been used. So in the St. Croix River Valley, the rocks that are related to the mid-continent rift are of two very different types. There's a lot of these lavas, mainly basalt, and I'll show you a couple pictures in a second. But there are also rift-related sediments that were deposited as the rift was sort of deflating, and the high topography was being worn down by rivers eroding the high rift valley. And some of you might know the Hinckley sandstone. It was quarried for a long time. That's one of these rift-related sediments. It's not the same age as the Cambrian sandstones. It's much older. It's like 1 billion years old. So the dells of the St. Croix themselves are primarily along the river, these basalts, lava flow upon lava flow that are also seen all up the North Shore, as I said, to some extent in northern Wisconsin, but especially over in the Keweenaw in the UP. And the famous potholes at Taylor's Falls are primarily in basalt. And basalt is a very hard rock, and it tells you the power of the glacial torrents that were tearing through that river valley late in the Ice Age to grind hard basalt down in this way and create these mortar and pestle-like potholes. And then we know that those basalts were lying at the surface at the time that those Cambrian beaches existed, because the very first Cambrian rocks in the St. Croix River Valley tend to be conglomerates, which have these big cobbles of the basalt that was becoming incorporated as the beach sands accumulated. But the first Cambrian units are often these wave-rounded conglomerates with cobbles of the basalt. And then, as I said, I guess I'm a little out of sequence. The rift filling sediments are just a little bit younger than most of those basalts, and the Hinckley sandstone was favored in the late 1800s and early 1900s as a kind of brownstone building stone. And my favorite building built of Hinckley sandstone is this Pillsbury Hall, which was until fairly recently the home of the geology department at the University of Minnesota, where I was an undergraduate. And when I was going there, it was a soot stained building. It was just kind of a dour black. And I don't know, 20 years ago, they sandblasted it and revealed that it's kind of a gaudy, showy Victorian building. It has gargoyles, but it also has this kind of checkerboard pattern because the sandstone has varying colors. But that's a mid-continent rift age sandstone, not a Cambrian sandstone. So let me pause and maybe I'll stop sharing for a second. And I'm very happy to answer questions. That was a very, very, very quick overview. But again, the big idea is that there are three big chapters with totally different stories: glacial, tropical beach, and then this major continental rift going backwards in time.
I'd like to ask a question. I'm a regional planner in northern Wisconsin, and one thing that's been brought up several times to me is the landform orientation. So Door County, Bayfield Peninsula, North Shore, Minnesota, Isle Royale, Keweenaw, all seem to be in a northeasterly, southwesterly orientation. Is there a geologic reason behind that?
In most cases, it's not the same geologic reason, but there's a geologic reason behind all of those, yes.
Okay.
So for example, the Door Peninsula, which is pretty close to me here, maybe I'll quickly share my screen and go to the Wisconsin geologic map, is part of the Niagaran Escarpment, actually. It's the rim. We don't have Michigan here, but imagine Michigan to the east. This part of Wisconsin is part of what's called the Michigan Basin, which is almost a perfectly circular bowl-shaped feature where all of the units, the strata, tilt very, very subtly, like less than a degree, inward toward the center of lower Michigan. And everywhere that this Silurian dolostone, which is a really tough, resistant rock, is exposed at the surface, we have what we call the Niagaran Escarpment, and that's the same step in the landscape that Niagara Falls falls over, way over in Ontario and New York State. So that's not a story that affects the rest of the Lake Superior region. It's a basin that's centered around Lower Michigan. Isle Royale and the Keweenaw are part of the Mid-Continent Rift story, and they are kind of aligned with each other structurally. The Lake Superior Basin is kind of like a giant, gentle U-shaped fold. These lavas actually did get slightly crunched and folded after the volcanism ended, and the two limbs of the fold are expressed on the two sides of the lake, or from the Keweenaw over to the North Shore in Minnesota. So yes, that alignment is very much structurally controlled by the resistant rocks of the rift and the way they've been kind of folded up. So usually there is some sort of geologic story, but it's probably not the same story everywhere. It's just kind of a fluke that these peninsulas are sort of the same orientation. Like the Bayfield Peninsula is made of partly rift-filling sediment and even Cambrian sandstone. So there's not really a direct connection to the mid-continent rift story. So that must have another explanation, maybe glacial. But that's a good
Perfect.
question. Yeah.
So it would be fair to say that in response to that question, that some of this is, yes, geologic, some of it is happenstance, just coincidental that these formations tend to be in the same direction, but
Yeah.
they're
It's
not all
coincidental
directly.
that, yeah, over such a wide area, but all of them have a geologic reason. Yeah.
Okay.
Hmm.
And one more question about glacial rebound,
Mm-hmm.
Lake Superior. I was at a seminar on the South Shore last summer, and we were looking at it was I believe it was the University of Wisconsin Superior that conducted the outing, and we were looking at some sketches of the rebound rates, and it was actually pretty surprising. I mean, it's a very small amount, but over time, as you said earlier, 10,000 years really doesn't mean anything in geologic time. That really seems to be impactful.
Oh yeah.
That that it could change the dynamic of Lake Superior quite substantially.
Yep.
But is that a, I guess from my question would be, is that a static process? Is that continuing at the same rate, or is it decelerating over time?
Yeah, it's slowing down
Okay.
because we're kind of retreating from the land or the mantle of the earth, remembering all that ice. But it's still going on, but the rate of rebound is slowing. Yeah. And I mean it's relevant even well away from where the glaciers were. So for example, in Chesapeake Bay in the Washington, D.C. area and Baltimore, that was not glaciated. But when the glaciers were here, the land just beyond the ice margin, which is this hand, was actually pushed up. So those areas like Chesapeake Bay were actually bulged up during the ice age. And then when the ice melted away, the land rebounded where the ice had been, but now those bulged up areas are going down and perceptibly so. And that's just making sea level rise even worse because not only is sea level rising, the land is sinking. So these things are happening slowly, but they matter in some cases, especially if you're already at or near sea level. In our area, I think the rate of rebound is now less than an inch per decade. I'd have maybe you have better numbers, but over time it's substantial. And in Norway, for example, there are kind of dramatic cases where there are Viking ship slips where they would slip their, big Viking ships into the water. Those are now standing like a meter above sea level. And the Vikings were not stupid. They knew where to put their slips. So that's 1,000 years ago, the relative sea level there was a meter different. So it's slow, but it's not beyond human timescales in a way.
I'm glad you brought that up. That was my next question. If there are other areas on the planet that are comparable in terms of glaciation that have had maybe a longer period of ice-free period where there's been more of a rebound.
Well,
And
Britain, some of the dramatic coastlines of Britain, you just think of British cliffs along coastlines. Those are largely an artifact of post-glacial rebound, just this, dramatic rebound of the land, stranding the land high and dry above the sea. So Scandinavia, Britain, Russia, all of these places, they see it. And I've heard that actually in the Baltic Sea, I think Finland actually has laws about who owns new land that emerges from the sea because of post-glacial rebound. That might be mooted again if sea level rise becomes faster than the rate of post-glacial rebound, then there's not going to be any new land. But I mean, it's an important enough phenomenon that they actually have legal rules about how to deal with it.
that's incredible. Is there I mean, considering the rapid advance of technology and now we have LiDAR and precision measurements can be taken, are we finding that these rates of rebound are different than what they may have thought of in the past just because of the new technology? I mean, has it improved the ability to measure things like glacier rebound?
That's a good question. I would think so. It's not my field. I know that we can actually measure plate motions in real time, and those are on the order of like centimeters per year.
Hmm.
So I would think we can do it in almost real time or averaged over, 5 or 10 year time scales with very high precision GPS, but I'm not sure.
Okay.
Anybody else? Gail?
Thanks. My question is kind of related to the plates. So as a kid, I just remember learning about, okay, there are these plates in the Midwest, and we never think about them. Can you point out on those maps where they are and just talk a little bit about them?
Yeah, we have some
And
major plate boundaries, ancient
yeah,
boundaries.
yeah.
Um, so yeah, this is kind of a complicated map, but so the really, really old, we call it the Superior Craton, is represented in Minnesota, and it continues up into Manitoba and Ontario. That's really the oldest part of North America. Then there's this, what happened to here we go. This Great Lakes tectonic zone is a major old plate boundary. It sometimes still has tiny earthquakes like magnitude 2 and 3, but about 2.6 billion years ago, the Superior Craton seems to have collided with this even more ancient crust of the Minnesota River Valley that includes rocks as old as 3.5 billion years old. And at least one time they were thought to be they were the oldest known rocks on Earth. We now know of rocks that are as old as 4 billion years, but they're still pretty old. And no one really knows.
Are they visible? Can we see them?
Oh, yeah, in the Minnesota River Valley, and they were quarried extensively in the 19 teens through 30s at Morton, Minnesota. Very famous building stone called the Morton Gneiss, if you Google that.
Yeah.
It was used all over the United States. I see it, and I'm always like, oh, I know you. Hi, Morton Gneiss. It was the Adler Planetarium in Chicago, many buildings in downtown Chicago, Milwaukee, Minneapolis.
And the plates, there's no chance of major earthquakes at all, or?
No, we are now pretty glued together and things are stable. But all of these black lines on this map actually represent ancient plate boundaries. And the Mid-Continent Rift, too, almost became a plate boundary and then didn't.
The other question I have, if it's okay, is if you could just talk about copper and how, you know, and just a little bit how that was formed or what it took to make that and how old.
Yeah, that's a good question. So up in the Keweenaw Peninsula in particular, the lavas of the Mid-Continent Rift, the basalts mainly, host the world's largest so-called native copper deposit, which means copper that is just as elemental copper, not bonded with oxygen or sulfur or whatever, just copper. And that is related to the Mid-Continent Rift story, but actually the probably faulting that happened during that folding I was talking about, how the Keweenaw Peninsula, which is here, and Isle Royal, which I can't quite see, which must be about here, they represent two parts of this big fold. When that folding and that closure of the rift happened, there was a major fault called the Keweenaw Fault that holds up the spine of this whole peninsula. And along that fault, fluids that came from the deep crust carrying copper inundated the rocks and left these deposits. And the deposits are primarily in the very frothy flow tops of the lava flows, where there was a lot of permeability, and then also in interbedded conglomerate layers that are between the lava flows. So we just know there was a lot of fluid carrying copper solutions going through those rocks over a pretty brief period of time, about 1 billion years ago, not long after the whole volcanic episode. But the volume of native copper that's up in the Keweenaw is also just kind of a mystery. Why so much there and not really in other parts of the rift? There are trace amounts in the North Shore volcanics and some others in Wisconsin, but nothing like in the Keweenaw.
And so we don't know what was really special happening.
Not really. I mean, there are many, many, many scientific papers that have been written, but I don't know.
Okay.
Yeah.
Thank you.
Great questions. So if you're still interested, I thought I'd read a little bit from my book. I've written several books, and this one is a little bit different in that it's sort of a memoir. I was actually a very reluctant memoirist, but I wanted to write a book that really took ordinary people with no background in geology deeper into the kind of way the planet works. Not just talking about the past, but getting a really strong sense of the physiology of Earth and how amazing it is that it's almost animate in some sense. So I struggled how to write a book like that didn't feel too textbooky. And finally realized that maybe I could use my own story as a scientist to welcome people in. And so the framework of the book are 10 rocks that either I was living on or kind of obsessed with or studying at different times of my life. And I'll just read excerpts from one chapter, but these are the different rocks. I don't know if it's legible enough. But the first two are sandstones, specifically the Cambrian sandstones I just mentioned to you. that I grew up on and before I became a geologist, and then basalt of the Mid-Continent Rift, which as a student at the University of Minnesota was one of my first rock types that I really got to understand scientifically. So I thought I would read to you from the basalt chapter and then a little bit from the prologue too, so that you get a sense of the book. This is the frontispiece for the book that shows, again, a geologic habit of mine. It's showing for these 10 rock types their original settings. So when we look at a rock, we understand that it signifies another version of the world. The Cambrian sandstones of Wisconsin represent, as I said before, tropical wave-washed beach. The basalts of the Lake Superior region represent a volcanic rift. Oh, and these are just to show the sandstones that I grew up on, the Red Cedar Trail. I don't know if anyone's ever biked or skied. These Cambrian sandstones are very important, not only in Wisconsin, but Minnesota and even Illinois. They're the primary aquifer for many, many people. And that's illustrated by the lower photograph showing great icicles. That's groundwater coming out of the banks in the wintertime. And then one of my favorite buildings in Menominee, where I grew up, was built of the sandstones, the Mabel Tainter Theater. It was actually the library too when I was growing up there. Okay, so I'm going to read a short bit from the basalt chapter and a little bit from the prologue, and then we can talk, and then we'll be done. Okay, chapter 2, basalt. 3 university vans, the old 15-passenger rollover-prone kind, are hurtling along Highway 61 on the north shore of Lake Superior on a chilly Saturday in May. I'm in the third vehicle, sharing the last row of seats with tents and sleeping bags jammed up to the ceiling. We'll be camping at the end of the Gunflint Trail on the east side of the Boundary Waters, close to the Canadian border. This is my first multi-day field trip as a geology major, and I'm just beginning to develop a sense for the norms of this particular subculture. I hear the teaching assistant, a bearish, bearded PhD candidate who is driving with alarming inattention, say that snow is in the forecast, and I curse myself for not bringing a better coat. It didn't even occur to me this morning when we left the balmy spring weather in Minneapolis. We're well past Duluth, and the few businesses along this stretch of road aren't open yet. The summer tourist season is still several weeks away. Our professor announces on the staticky walkie-talkie that we'll make a rest stop. So the vans pull over to the shoulder of the highway, and the 30 of us unfurl ourselves into the bracing air. It's 1981, and the oil industry is booming. Geology departments everywhere are bursting with students. Geology majors could land high-salary jobs in Texas and Louisiana in oil and gas exploration with even a partially completed bachelor's degree. The men in our group quickly relieve themselves by the side of the road without a hint of self-consciousness, while I and the other few women in the class glance at each other uncertainly. There's no spot that will be out of view of the others, especially since the guys are now fanning out and heading down to the Pebble Beach. In wordless consensus, we decide to hope for a bathroom somewhere soon and join the professor and our male classmates by the shore. Our small miseries are soon forgotten as the big lake starts working its charms on us. Its vast, wild solemnity compels our attention. Lake Superior is the largest in the world by area, containing 10% of all the fresh water on Earth's surface. It creates its own weather patterns, and its tempests have swallowed at least 500 ships whole. Today, though, the water is fairly calm. We can just make out the low silhouette of Isle Royale on the horizon to the northeast, but the far side of the lake, more than 200 miles away, is hidden by the curvature of the planet. The water is brain-freezingly cold, and with air temperatures in the 40s, no one is tempted even to dip a toe in. Yet we all feel some visceral need to interact with the magnificent, mysterious expanse of water. The guys start gathering flat stones for skipping, falling comfortably into habits from boyhood. I walk along, picking up unusual-looking rocks, knowing that there could be quite a variety here, gathered from a wide swath of Ontario by glacial ice. Soon I've amassed more stones than I can hold, and am certain that there are some rare finds. One is almost sensuously smooth. Forest green. One is like a rigid, rusty sponge full of spherical holes. A third is somber gray, but gaudily polka-dotted with orange crystals and starburst patterns. Then I spot a familiar friend from childhood, a dark gray rock with white lines, an example of what we called Chinese calligraphy rocks when we would find them in the gravel pit near our house. Their needle-like crystals seem to encode messages. Perhaps now, at last, I can learn what their inscriptions mean. Our professor is looking out toward the lake, apparently in no hurry to move us on to the next stop. Back on campus, I'm generally too timid to ask questions in class and could not imagine a one-on-one conversation with a faculty member during office hours. But here in the presence of this great lake, whose immensity flattens human hierarchies, I'm bolder. I show the cobbles to the professor, a soft-spoken man whose meandering lectures both reflect and obscure his deep knowledge of Minnesota's geology. He looks quickly at my collection and says, "This one's basalt, so are those two. Same for this porphyritic one with the long crystals of plagioclase. They're all local basalts, haven't traveled far." All basalt? I received this news with a strange mix of emotions. First, embarrassment. This is an intermediate level course in igneous petrology, the study of rocks formed from magma, and even a student in an introductory class would know that basalt, the volcanic rock of Hawaii and Iceland, is among the most common rock types on Earth. How stupid of me. It's as if I've missed a basic vocabulary word on a language quiz. Next comes a burr of irritation, perhaps akin to what people learning English must feel about wildly inconsistent spelling and pronunciation rules. None of these look like the basalt specimens in the classroom. How can one kind of rock have so many different appearances? Then comes a shadow of self-doubt. Maybe I'm not cut out for geology. I just don't have an eye for rocks. Yet once my wounded pride has recovered, I feel a nascent shift in perspective. The calligraphic or porphyritic rocks we treasured as children were more than mere curios. They were legible records of a vanished world where black lavas oozed from subterranean fractures. The characters in the rock were clumps of slender crystals that had formed in a subterranean magma chamber before being swept to the surface in an eruption of liquid rock. I had sensed that these stones had secret wisdom to share, not realizing that they were remnants of a great volcanic empire. Now it was suddenly obvious to me that all of human civilization was perched on top of ancient geologic kingdoms. So I thought I'd read just a little from the prologue because we kind of zoomed in quickly, but that's the mid-continent rift. All of those rock types are ones you've probably seen. Maybe if you hunt rocks in gravel pits, you see a lot of this sort of thing. These were the ones we would call Chinese calligraphy rocks when I was small, but they represent, again, large crystals that were forming in a magma chamber, and then when an eruption happened, they got swept out with the still liquid rock and formed these amazing patterns. Here's a typical North Shore volcanic basalt with gas bubble holes that we call vesicles. Many of them, though, are just massive and fine, like this one. And this one isn't actually one I found. I couldn't find a nice specimen. I found this picture online, but this is Thompsonite, which is very classic mineral that can form inside these vesicle holes in a lot of the Lake Superior basalts. So a bit from the prologue. This book is an invitation into my geocentric worldview, in which rocks are raconteurs, companions, mentors, oracles, and sources of existential reassurance. To me, rocks have distinct personalities. Each type has its own idiom. Some are extroverts, easily read and eager to share, while others are reticent and cryptic. Some are like celebrities, famous and beautiful, but of little functional importance to the world, while many that seem plain and dull are essential to the long-term stability of the planet. Each chapter in this book features a rock type that was a protagonist at a certain time in my life, from an insular girlhood in northern Wisconsin through an unlikely vocation as a geologist studying mountain building processes in remote parts of the world. With each chapter, the stories of the rocks become more complex and my relationship with them more intimate. In sharing my small human story, I hope to convey the grander dramas embodied in Earth's pantheon of rocks, and to show how rocks, whether one ever thinks about them or not, ultimately define reality for everyone who lives on this rocky planet. While not everyone can or should become a geologist, geologic habits of mind, an instinct for Earth's rhythms, a feeling for our place in its story, are essential to the physical and psychic well-being of humankind. Around the time of the Industrial Revolution, Western society stopped seeing the earth as imbued with wisdom, offering, in Shakespeare's words, books in running brooks, sermons in stone, and demoted it to dumb matter that we could outwit and exploit. This view of Earth as inert and unresponsive has led not only to environmental catastrophe, but also to cultural anomie. We Earthlings don't remember who we really are. Contrary to their reputation, rocks are alert, responsive, communicative. They are the force field in which we live, the infrastructure of our existence, playing central roles in the economy of the world as aquifers, architects of topography, managers of ocean chemistry, regulators of climate. They are also shapeshifters and fortune tellers. Once one becomes attuned to the language of rocks, it is obvious that Earth is vibrantly alive and speaking to us all the time. So here's a crass commercial message. These are my earlier books, and this one is the one I've just given you a little glimpse of. So I will stop there. And again, happy to answer questions, specific or general, about geology.
I'd like to ask a question about one of our locally distinct landforms here in Northwest Wisconsin. We have an area that's referred to as the Blue Hills or Barren Hills.
Yeah, I've been
Yeah.
there.
Okay, it's really distinctive in comparison to the surrounding areas. Felsenmeers are relatively common. Just the topography, terrain is very, very distinct and different. Can you give just a brief rundown on what is occurring here, what happened here to create this unique landscape?
Yeah, and I'm not an expert on this, but I know some. And so this word Felsenmeer is German, and I think it means something like sea of rocks. So these are places, they're usually moderately steep slopes that are mantled with just broken rock that has nothing growing on it. And in the Rusk County area, which I think most of these occur in, the rock is quartzite, which means it's metamorphosed sandstone. So it would have been sandstone deposited in the Precambrian, and then baked so that the quartz grains are kind of fused together. And that particular rock type really doesn't have anything to offer most plants. Even lichens have a hard time growing on quartzite. It's just silica, SiO2, which is what quartz is made of. And so it's just not a very hospitable substrate. And often in that Blue Hills Felsenmeer place, I've been there and tried to walk. It's very, very difficult. The rocks are very precariously stacked on each other, and when you start walking around on them, they're kind of rotating and things. So I think anything that gets started gets thwarted when a rock topples over and a different side is exposed. So my understanding is that those are essentially fossil talus slopes. A talus slope is like usually in a mountainous area where freeze thaw action is very intense and slopes are fairly steep. We don't have too many of those kinds of talus slopes in Wisconsin because we don't have mountains, but they're relict sites from the Ice Age where even a modest slope with rock exposed could have developed just this kind of apron of rocks at the base. And because of the nature of the rock type itself in Rusk County, just nothing has ever grown on them. At Devil's Lake State Park, there's quartzite, the Baraboo quartzite. People have probably seen that. And there are fossil talus slopes around Devil's Lake, the tumbled rocks that the WPA built these beautiful trails on. But that's the only other analogous site to some of those Felsenmeers in Rusk County. So that's my understanding broadly. Now, why nothing really has ever grown on them, I don't know. But they're quite weird. I agree.
It creates a very visually distinct but a distinct landscape, but it's also from a flora and fauna standpoint. It's interesting you mentioned that lichens don't grow, and that's one of the first things I noted that they're just bare exposed rock,
Yeah.
uh, but provide some unique habitat for snakes.
Ooh, I'm
If
glad I didn't.
What
uh,
kind of what kind of snakes?
all kinds of snakes, you name it. I've seen everything that is endemic to our region in these Felsonmeres come out to warm up in the spring, and I suppose the rocks heat up and they just
Yeah,
enjoy
once
that.
they get warm, I can imagine. But they're also kind of. I've been there in like well, early spring, and it's like a microclimate too. That there's snow and cold air circulating under that stack of rocks. But once rocks warm up, then they really retain heat. Yeah. Ooh, that makes me feel a little bit different about walking around.
Is that quartzite is different than pipestone, correct?
Yeah, although it might be, I mean, there's pipestone in that area too, and it's broadly the same age, but the pipestone is clayey,
Hmm.
and the quartz site is silica, it's quartz. So they're mineralogically different, but they're part of the same sedimentary package, and they're probably the same age as the Baraboo quartzite, actually, in southern Wisconsin.
Hmm. Fantastic. Thank you.
Yeah. Geology, Wisconsin has amazing diversity of rocks. People don't realize this. I say we have geodiversity. um, and we also have better exposure in general than Minnesota. On the lakeshore in Minnesota and on the St. Croix in Minnesota, and then down in the driftless area, you can actually see rocks, but pretty much like anything west of the Twin Cities, there's very little rock exposed. So Wisconsin, by comparison, has a lot more visible geology to see and a lot of diverse ages and types of rocks. So, yeah, people should plug into the Wisconsin Geological Survey and Minnesota Geological Survey. They've got lots of great resources if you're curious. Gail.
The title of your one book, and I'll have to read it, but I wonder if you could just give me a synopsis. The subtitle was what caught me, was something to the effect of um, how thinking like a geologist,
Oh,
how
can help.
thinking like a geologist can help save the world. And you really talk about rocks as a living creature, almost a sentient being, but
Yeah, I mean, I feel that way as a structural geologist. I study mountains and how they grow. So, rocks are truly animate to us who study tectonics. They're moving around, they're nimble. Um, so that is kind of a theme that runs through my new book. Timefulness, as the title suggests, is really trying to get people to understand um, time as another dimension almost. I think many of us geologists feel that way. It is a fourth dimension, and developing some kind of depth of field, the relative times, like the glacial time in Wisconsin, the sandstone time, the mid-continent rift time, not collapsing everything into just prehistory, having
Yeah.
some sense of proportion, but also developing an appreciation that these things actually are still with us. They shape the landscapes we live in, the resources we have. They're not irrelevant and arcane. And I think geologists have not, in general, done a good job of conveying that this is not just obscure knowledge. If the average earthling understood better the way the earth works, we'd all be better off. I sometimes say most of us are like bad tourists on earth, never actually learning the language or the culture of the place that we're going to spend our entire lives. And most of the environmental problems we have arguably are because of that. So I'm a bit of a geo-evangelist, but I try to make the content accessible and feel relevant. It's not just this kind of arcane academic pursuit. It really does matter.
yeah.
And it's not all about dinosaurs. That drives me crazy. So it's almost 8, and I don't want to hold people, but thanks for having me.